Here I have two SDR-IP units. They are both running phase locked to 10 MHz references and looking at the same signal, the signal from the Wenzel oscillator. And here is the result on the Linrad screen. The green track is the average correlation spectrum between the two units. And here is the noise within about 100 Hz bandwidth. And the noise level is minus 146.05 decibels per hertz. And the correlation gain here is 23.06, a little bit noisy decibels, and the theoretical limit for correlation gain is 29 dB, so this should be a fairly accurate reading. 146 plus 23 makes 169. At the same time, I have been running the same signal on the M-track quad and the mixing down to low frequencies. And here I have a similar number of correlation averages, 940,000. The SDR-IP was 861,000. Here you can see the noise is flatter. The correlation gain is only 20.4 or 20.5 maybe, and the noise floor is 148.6 plus 20.4 is 169. So it seems this is fairly accurate, and that the SDR-IP units can be used at a wide range. Now the SDR-IP is quite noisy at close range. You can see the red noise floor is at frequencies closer than 2 kHz. The white track represents the noise floor. It goes up here. You can see that the correlation spectrum stays the same up until about here, while it becomes more and more noisy. And even closer it goes steeper upwards, and I cannot say whether it's noise from the SDR-IP or from the signal source. I could maybe, if I go for the other measurement with the sound card, so I haven't evaluated, but you can see here it is much cleaner, and probably the noise floor I can see here is reasonably accurate. I have increased the bandwidth to about 400 Hz, and I remeasure the noise floor here. And now it is minus 146.08 dBc per Hertz with 23.25 dB for the correlation gain. And I done the same with the sound card measurements. The noise floor is 148.5 and correlation gain 20.61. Both measurements add up very close minus 169.2 dBc per Hertz is the average. That's the noise I find for the composite noise of this Wenzel 501 25420 oscillator. Here is the current setup I'm using. Reference oscillators, one here and one here. And amplifier and a coupler minus 8 dB to get the reference signal for the SDR-IP on channel 1. And then a 20 dB coupler followed by an attenuator and an amplifier. That is to isolate the oscillators from each other. Mixer and PLL amplifier. So the other channel coupler here, also 30 dB attenuator and an amplifier. The two oscillator chains, LO, amplifier, coupler, and coupler, they are equal. And then the receive system is an hybrid to split this oscillator into two at the level of about 23 dBm. And the signal comes from down here, has a stepped attenuator everywhere to set the level very close to attenuation for this channel. Then there is a hybrid to split mixers at 23 dBm, sending a signal into the M-track quad. There is a amplifier between that I forgot to draw in this figure. So I added it here. And this and that part are equal. The SDR-IP channel 2 reference comes from here and is well isolated from the other reference. So they don't have common sideband noise. They are independent down to frequencies in the order of 0.1 Hertz or even below. The RF signals, they have couplers here and here. Maybe there is some leakage of oscillator signals this way that could cause extra spurs in the SDR-IP. Although this is a directional coupler, so the signal going out this way should not be very strong when it comes from the coupler into the attenuators, these two that are used to set the level for the SDR-IP units to become close to saturation. Several hours have elapsed, so I make a new measurement of the noise floor, 146.08, and the correlation gain is 23.20, and that is for the SDR-IP units. For the sound card, correlation gain is 20.57, and the noise floor now is 148.526. The general picture has not changed. 169.10, I had 169.12 about 6 hours ago. And the SDR-IP changed a little bit more, 169.33, and now 169.28. The difference between the two different measurement methods is 0.21 or 0.27 decibels respectively. And I think that is a difference between the systems and not only statistics. But I don't know. There was many hours before this 6 hours, I have forgotten, but maybe 2 days or so. I will expand the spectrum to look a bit more close at the spurs in the SDR-IP systems. So I can expand a couple of times. Like this. And I see there are many spurs. But there is a significant measurement on the noise floor at this frequency. The carrier is here. As you can see, it reads 0 here. The channels differ by 0.09 decibels. And the noise floor here, and I have to have a better resolution in the baseband. Sorry, that's not possible maybe. I didn't intend to do this when I set up the parameters. And as you can see, I cannot measure the noise floor here. And that's because I didn't set a suitable window function and also a too high sampling rate for the baseband filter. But what I can do, I can look at the green trace here and read it out manually. It comes at about 17 decibels. And then I had in the previous measurements, which I haven't saved, I think, but I can look back in the video and see at what level the noise floor was at 4 kilohertz, and that's minus 169 decibels. From this video, maybe half a minute ago or so, I can see that the green trace is at the second line from the bottom. And that is minus 5 decibels on the vertical scale. 17 dB that I saw on the scale is 22 decibels above minus 5. Which means that I see about minus 147 dBc per hertz. This is at an offset of about 30 hertz. Now 17 was maybe a little bit optimistic. 18 or 18 and a half is perhaps better. But I don't have the resolution to say much based on this measurement. But it's hope. It gives me some hope because it is not the noise, it is the spurs that constitute the main problem with this SDR-IP. And maybe I can find a reason for why there are so many spurs. I have set the parameters for the main spectrum waterfall and the main spectrum to look similar for the sound card measurement and the SDR-IP measurement. And I can see one very interesting thing. All these close-spaced spurs, I have here, for example, strong ones, equally strong as this. This is correlated the same in both SDR-IP units, but these ones are not. They are not correlated, they are much weaker in the correlation spectrum. So the noise floor is clearly well below these peaks, while it is at this peak. This one, I have some understanding what it could be. It is because of the reference, which is 10 megahertz, which is here, and then there is this signal, and there comes a mirror image somehow from the digital processing, or maybe from the sampling itself in the AD converter. It samples at 80 megahertz and 10 megahertz is a subharmonic. Anyway, these spurs are present in the sound card and they are correlated in the SDR-IP units. But these spurs, the green here, they are something else, and I will see if I can find out. There are different firmware versions in these two SDR-IP units, so that could be a reason. Restarted with different parameters for the baseband here. Now I am tuned on the carrier to read the carrier level, which is still 0, as should be, because I didn't change the first FFT parameters. Now I look at the noise floor here, about 20 Hertz above. You can see 10.000 and 400 microhertz away. So now I jump about 20 Hertz, and it says 98, so that was correct. And then I can look at the noise floor at this point, and I cannot trust the correlation data from here, because the resolution in the main spectrum does not resolve the narrow carriers that are the problem in this situation. I have expanded the baseband scale in frequency, and it is clear that the close-spaced spurs, they are at is it 1.7 Hertz or so? They are present in channel 1 only. Channel 1 has the oldest firmware release in it. I will save this and try to set other parameters for the SDR-IP units. I have changed the center frequency by 10 kHz upwards, and then tuned in for the signal, and this has removed some of the spurs. Here is what I had before, and you can see the spurs at far away, they have gone, these correlated spurs, but the close range spurs, these ones, they are not very different now with the new center frequency. I have been using these parameters for the SDR-IP. The dividend 100 for a frequency of 80 kHz. I have changed that to 64 to make it a power of 2, which could be easier for the FPGA to manage. This is 125 kHz sampling rate. And here is 80 kHz. And the width is a little bit different, but it looks very similar, the structure. And if I look at the baseband, maybe like this was 80 kHz, and here is 125. It's just expanded a little bit because scales go in factors of 2 in Linrad. I want to compare the close range measurements from the sound card and from the SDR-IP. And while doing so, I see this. You can see the higher noise floor here. That is the sound card, and the reason is most probably poorly cleaned connectors on the oscillator chain. That will not affect the result on the correlated noise. It will just degrade one or the other of these curves. I will not correct that now, because that would interfere with the measurement on the SDR-IP, which has been running for 19 hours now, and I want some more hours. This has only been running for half an hour. The sound card is much better at close range, which is obvious. As you can see, the correlated trace comes very close to the direct measurements. while on the SDR-IP there is need of correlation gain. The sound card seems to give a reliable measurement up to about 15 Hz. I can see, for example, at 5 Hz it shows -139. The SDR-IP at 5 Hz, here is 139, but the measurement shows 133 or so. And it's clearly spurs because the curve is going up and down. And then the phase angle of the spur is changing, so it comes with a negative sign here. 11 Hz -152. 11 Hz -152. And it's clearly not correct. And then it goes up again, and I can see from the imaginary part here there are peaks up and down and up and down. So the phase angle of the spurs varies, and maybe the result below, let's say 2 Hz or so, could be okay. The baseband filter bandwidth with the SDR-IP is about 1 Hz. This means I cannot go closer than about 1 Hz offset to measure the phase noise. But 1 Hz here I can read -115. The sound card I can have a much narrower filter. It's half an Hertz. But I can read at 1 Hz -115. So in order to make the bandwidth much narrower for the SDR-IP, I will have to change the coding of Linrod to allow much larger first FFT transforms, because they have to span, the saved transforms have to span a larger time to allow a narrower bandwidth here in the noise graph. It would be interesting to compare the noise at the separation of 0.1 Hz or so, but that requires reprogramming Linrod, and it will take some time because I have forgotten most of how the code is written. Here is phase noise up to 1.5 kHz. And I can see up here I have reached the limit for this measurement time, 68 hours actually, because the imaginary part is equally strong as the real part. And something is a little bit odd with that, because the correlation gain, that's the distance from here down to the red part, it is larger than what it is here. So there is a problem of some kind. I cannot trust this kind of measurement. Now, if I go for amplitude noise, you can see that the amplitude noise is equally strong in the real part as in the imaginary part. The amplitude noise is very low in the SDR-IP. So the problem with the unit could be some digital noise on the control input of the crystal oscillators, the PLL input. One very interesting thing is the level of the uncorrelated noise. I mean, this here. This is phase noise at about -151 dBc per Hertz at 1.5 kHz. 151. Now I go for AM noise. And it comes here at about -142. And it doesn't slope very rapidly. At 500 Hertz here, it is at 133 139 perhaps. So I go over to the phase noise again. And it is about the same or even lower, the phase noise. On one channel the phase noise is about 144 and we see spurs. So actually the noise is down here somewhere. So what I can say is at close range, let's say up here, the phase noise is low, but the spurs are high. And the spurs are frequency modulation. While when I go for the AM noise, it looks like this. It doesn't have any spurs. So the AM noise is likely noise on the reference voltage input, and that is random noise. It could be the chip itself or maybe something with filtering. But phase noise, that is probably the PLL input. I will try to see if I can see something directly on the inputs to the chip. Here is the inside of the SDR-IP. I have placed a 10 microfarad tantalum capacitor from the PLL input of the oscillator and then connected to the oscilloscope. I have also a 1 kilo ohm resistor that I can connect to the oscilloscope side of the capacitor. That will reduce the AC voltages on the PLL input of the oscillator. This is the oscillator that is being used in the SDR-IP. And here is the data sheet. It says SSB phase noise at 10 kHz is typically minus 90 decibels per hertz at 100 megahertz. So that is 110 at 10 megahertz. And that is far from good enough for what I'm doing. Here is the Linrad screen when I'm running it without any modification. This is what I see at the control input. It is not 5 millivolts as the oscilloscope tells me, because there is a 20 dB amplification. I am running the signal into channel 2 and taking out an amplified signal and put it back to channel 1. So it is about 0.5 millivolts per division. So there is a 1 millivolt AC on the control input. Now I can put this resistor in contact with the capacitor. Now I have connected the resistor from the capacitor and oscilloscope to ground. The AC voltage on the control pin is reduced significantly, as you can see. And on the Linrad screen, things look much better. The noise floor is lower and the spurs are gone, and these strong spurs are much weaker. But the close range noise is stronger because the PLL gain is lower now. And I have to trust the performance of the oscillator more because the PLL is doing less. So it would be nice to get rid of these spurs by doing something on the PLL circuit. The PLL is done with this IC, an ADF4002. And here is the description. And I haven't found out yet how it works, why there is low frequency signals from it, I think it should only run with 10 megahertz and 80 megahertz. There is no reason to divide down to lower frequencies than that. But I don't know. Maybe there is simply noise from the digital things here coming into this extra board that is doing the PLL. I don't know. I will try to find out. The DC supply for the PLL board has a filter, a capacitor, an inductor, and a second capacitor. I'm looking at the voltage between the second capacitor and ground on this PLL board. And here is what I see. It looks very like the problem that I'm having. I added 4,700 microfarads, and it doesn't make much of a change. There is still a very significant low frequency modulation on the power supply. While looking at the spectrum here, if I remove that capacitor, like that, it's obvious that it helped for the higher frequencies, but not for the lowest ones. The board for locking to 10 MHz takes half an amp on startup for heating the oscillator, and then about 200 milliamps when running continuously. To do filtering with passive components takes big components. Here I have 4 times 4,700 microfarads, and the inductor is 400 millihenries. Now it looks like this. The frequency is about 4 Hz, but now it doesn't contain high overtones anymore, because it doesn't have this very sharp onset. So I have spurs every 4 Hz up to maybe 50 Hz or so, but there shouldn't be anything more above, let's say, 100 Hz originating from the power supply to the board. Here I'm looking at the separation of 30 Hz. And I have these spurs that are separated by about 10 Hz. I don't know where they come from. But the finer spaced spurs are gone now, and it looks much cleaner, as you can see up here. I have disconnected the 5-volt supply pin from the oscillator here, and I'm running 5 volts directly from the 5 volts of the board coming in here. And then I have removed the 10 microhenry inductor and put 10 ohms instead, so I can have an RC filter with a big capacitor. I have one capacitor of 4,700 microfarads right now, and I have arranged so I can easily connect 3 more equal capacitors. Going from here to here is what happened when I made that capacitor 4 times bigger. So these weak spurs, they are gone. This one is very weak now, and this is in the center of the filter. It has become weaker, and when I look here I see about 6 decibels. That's 4 times. So I would like to have significantly more capacitance, because this is an offset of 4 Hz or 5 Hz maybe. And it is going to be correlated with the spur in the other SDR-IP that I will use for correlation measurement. So it would be nice to get rid of it. I have disconnected the cable to the 10 MHz reference. And now I connect it. And the frequency jumps a bit. But there is a significant difference in noise close to the carrier, as you can see. This is the carrier, and here it is now. And at wide range, of course, there is no difference. And the spurs, the number of spurs is roughly the same, I think. And I place the carrier at a similar place. I have the spurs in a similar fashion. There was a flea market in the local radio club, and I was lucky to find a lot of these capacitors. They come in very handy now. I'm now running two SDR-IP units. One is the one I just modified, and the other is an unmodified in its original shape. And you can see the red trace has a lot of spurs, while the green does not have. I can change the polarization so I show the other. Now those that were green are now visible in the waterfall. And it's unclear whether the noise floor is different or not, but the number of spur is colossal here. But I do have spur here in the modified unit. There is a limited number of capacitors that I can fit into the box, and that I have available also. It's interesting to look at the correlation spectrum. I have set up now the modified and the original units. And you can see the spectrum of the modified one and the many spurs of the original. It will be interesting to see whether there are spurs in the correlation spectrum, the yellow here. I have to wait some time for that, but if they are very difficult to see, they will be suppressed equally much as they have been when this is also modified. But it's interesting to see whether they are present or not, and certainly when I go close and look here around 5 Hz, there will be a correlated spur, I think. Now I'm looking at the close range up to 80 Hz. There is one strong spur which is present in both units. The blue curve is the modified one, and the red curve is the one in the original shape with all the spurs. Both units have a spur at 48 Hz. That is the difference frequency between the 10 MHz reference and the signal under test. And they are similar in both units. The yellow trace is the in-phase correlation, and the red dots are the 90-degree out-of-phase component of the correlation, which means they are reasonably similar in amplitude, so they add together to come close to the red signal here. Anyway, this is present always. The problem that I'm trying to eliminate is the higher spurs. This is 5 Hz. That's difficult to suppress just with an RC link. And maybe it comes also from feeding the oscillator without filtering. The overtone 10 Hz comes here. This is suppressed by 5, 10, 15, 20 decibels. But there is a 90-degree shifted also, so that means 17 decibels for the power. Modifying the other unit also should lower it by 17 more decibels, 10, 17 down here, so it will still be a significant interference for measurements, but the noise floor between the spurs and closer to the carrier may be reasonable, although a lot of correlation gain will be required because the noise floor is only at minus 117 here at 3 Hertz. What I see is this, the carrier is at 0, and this is suppressed by 110 decibels. Then I can see that this signal, this spur, is surrounded by odd overtones to that 5 frequency. It comes here, and it should come here, coinciding with this. We can see maybe a double peak there. And this thing, I don't know what that is. Anyway, this modifying the second unit also should be very helpful. I have expanded the frequency scale up to 1.45 kilohertz, and here the noise floor is fairly flat at 169 dBc per hertz, and that is expected, but I can come closer now, maybe 500 hertz, 167 or something like that. Now I have modified the second unit also. It differs in the color of this digital board, otherwise they look very similar. Here is what the phase noise spectrum looks like now. It is only 3 hours 49 minutes, and I can read well noise down to about 600 Hertz. 4 times longer time, and then I can go down to maybe 400 Hertz with a reasonable statistical certainty. I can compare this with what I had before I modified number 2. It looks like this, and now like that. The big differences are down here, of course. For the close range, I would need higher resolution and more averages, which means much more time. So I will not try to look at that before I have done some other investigations of possible improvements. One of the things is this blinking looks like maybe 5 Hertz. That is a significant current, probably. So changing those diodes could reduce the 5 Hertz spur and its overtones. It's strong, the third order, at 15 Hertz also. 5 Hertz, 15 Hertz. I have reduced the AC gain for the PLL loop with a 6.8 microfarad tantalum capacitor and a resistor with 2 kilo ohms. And this is what I see now. The previous recording, that was a much longer time, look at the red and blue, or magenta and blue traces. This is with the original loop filter design, and here I have reduced the gain. That is a good thing at above, let's say, 25 Hertz or so, but it degrades very close to the carrier. I will have to study that separately, but the very close range I have with the M audio, so I'm interested particularly in getting a better performance at, say, 100 Hertz and above that. Here I'm looking at the 5 Hz spur. It is similar in amplitude in both channels, and it is out of phase between the channels. The strongest signal is in the red dots, and they go up all the way here. And I suspect this blinking LED to be the source of that signal. The 5 Hz spur is still present, even if I have removed the current from the LED, but it is attenuated from here to here. The imaginary part is significantly lower, so it is about 5, 10, 15, maybe even 20 decibels. I have changed the series resistor for the LED from 150 ohms to 4.7 kilo ohms. That's a factor of about 30, so the power should be 30 squared, or about 1000 times lower now for the 5 Hz spur. And that's 30 decibel, and I think that's enough to bring it down into the noise. I can still see the green light blinking, but it's weak now as compared to the other one. But this is good enough, and it will improve the spur situation. The optimum RC link to put on the PLL input of the oscillator seems to be 3.3 kilo ohms in series with 6.8 microfarads. Making the capacitor too small creates stability problems, and making the resistor smaller will degrade the performance at very low frequency offsets. Now both units are modified the same way. The blue trace is my old unit with serial number 0, and the magenta trace is another one that I bought recently over the internet, and it is serial number 4. And I noticed that I cannot optimize the added components in the loop filter, the PLL loop filter, the same way. The optimum I can find is slightly better than this, but not at all as good as the newer unit. So I will remove some of the capacitors here to see whether that is really so harmful. Now there are only 3 capacitors in place for this unit, and the change was made here, and that isn't really visible. And I don't see the spurs that should have come up. They are still below the noise floor. They could be harmful when using the unit for correlation measurements, but I need these capacitors because I have a third unit and I will try them on that one. Here is the unit with serial number 5. I have fixed the current for the LED, but I have not done any other modification to it. And here is what it looks like. And you can see below about 40 Hertz it is slightly better than the modified unit, but above 40 Hertz and particularly around 100 Hertz the difference is significant in the noise floor. And on top of that there are many spurs, as you can see, strong spurs that would be problematic for correlation measurements. We can see this one, for example, is still present in the modified unit. So I will do the other modifications also to this unit to see whether it becomes equal or different from serial number 4. The RC filter for the PLL circuitry on the reference clock board is added now. And here is what I see. At very close range, the red trace is a little bit worse than the blue, and the blue is the one I'm working with right now. The 3.3 kilo ohm resistor and 6.8 microfarad capacitor are now in place on the PLL input to the crystal oscillator. The change of the PLL loop that was so good for the other unit isn't quite the same here. I can see this peak at about 20 Hertz, and then it is a little bit better than the red trace at, is it 70 Hertz or so? And then the level of noise is a little bit higher at a higher frequency offset. This could be due to the oscillator itself, but that is the PLL loop. I will try to modify it, changing the resistors or the capacitor. I have reduced the capacitor by a factor of 2 by connecting 2 of them in series. This is worse than before, and this is easier seen here as the noise sidebands that come up here. And that is clearly the wrong direction. There are now 2 capacitors in parallel instead, and I think that is a trifle better. You can see the noise here, and it's a little better here. What happens very close to the carrier is another thing that I don't know right now. I added 2 kilo ohms in series for a total of 5.3 kilo ohms, and there are still 2 electrolytic capacitors in parallel for a total of about 13 microfarads. Here is 6.8 microfarads and 10 kilo ohms, and that is a little bit too high. The noise floor here has lifted, so it's the noise from the PLL circuitry that I have to attenuate a little bit more. Here is 6.8 kilo ohms and 6.8 microfarads, and I don't think I can do it any better than this. I have been running Linrad in correlation mode 1 with the 2 SDR-IP units for a couple of hours now in order to look for spurs. And I'm looking at about 60 kilohertz bandwidth, and I see correlated spurs here. The green dots. I have a correlation pair here, but nothing in the correlation spectrum. The reason is there are 2 spurs, one in channel 1 and another one in channel 2, and they are not correlated, so they disappear in the noise. But these ones, they are correlated, and they are far below the noise, 10-15 decibels approximately. They seem to be spaced by about 500 Hertz. I have changed the center frequency by 1 kHz upwards from 10.0 to 10.001. This has increased the number of spurs quite a lot, and many of them are correlated. You can see green dots high above the noise at many places. These 500 Hertz seem to have a similar level as before. I have not been running for a very long time now. These things will be easier to see if I set a larger bandwidth for the first FFT. With a 20 times larger bandwidth, the noise floor is 13 decibels higher. That's the white trace. But each spur now has several pixels on it, so it's much easier to see them. And you can see there are many green peaks, and they are not so weak anymore. So the selection of the center frequency is very important. You can see. And I see them also in the waterfall, some of them. And the level is the same as in the previous section, as seen in the baseband waterfall, which I haven't changed. Here is the Wenzel oscillator again. The frequency range is now from 9.97 up to 10.05 megahertz. I'm looking at the noise floor now at 50 kilohertz offset. And what I see there is minus 151.7 for the white trace. That's just the normal average noise floor. The correlation spectra, the yellow, is the average of 9,000, the 9,000 latest correlation spectra, while the green trace is the average of the latest 900,000 averages. So it is 20 times better statistics, but as you can see, the value doesn't change much from yellow to green, except near the center where the white trace is much higher. There you can see the difference of collecting more averages. In this video I have been using this Wenzel oscillator up till now, but now I have changed and I have connected instead this old oscillator of my own design. It uses many standard crystals, fundamentals on 10 megahertz. It has an extremely low noise floor at wide separations, but it is not particularly good at close range. The SDR-IP units have been running with this signal for a little more than 24 hours. The correlation advantage here is 31.7, but the theoretical limit is 35. So it means I have reached the noise floor, and that is the noise floor of the system, not of the oscillator. I'm pretty sure. I have to check it, but I'm rather certain. And I can conclude that, for example, by changing the frequency. And then you can see the correlation advantage changes. And at 50 kilohertz, the noise floor is minus 151.6. And the correlation advantage is about 31. So that means minus 182.5 dBc per hertz as the limit for this system of mine. I will remove the signal and not change calibration or anything else to see where the noise floor is when there is no input signal. There was some noise here when I switched off the power supply for the unit, but now the noise floor I see is minus 151.8. That is a difference of 0.2 decibels. And it will take some time. I have now 20 dB correlation advantage, and I will wait until tomorrow to see where the limit is. The noise floor now is minus 151.88, and the correlation gain 34.6. That is about minus 186.5, which is clearly lower than what I saw before when the signal was present. And further, the spread between the dots here in the yellow and in the green is equal, which means I haven't reached the system noise floor yet. So the conclusion is the noise floor is significantly higher when the test object is connected. So there are three possibilities. There is sideband noise from my oscillator, or there is phase modulation on the clock input to the AD converter, or there is amplitude noise on the reference voltage to the AD converter. To check whether the noise comes from the oscillator or from the SDR-IP units, I'm using these boxes with an attenuator to get a good 50 ohm load and 10 decibels attenuation 50 kilohertz away from the carrier, and a very deep notch on the carrier. This way I can increase the gain for the SDR-IP units, so the noise floor from the oscillator will be lifted while the carrier is weak. I can now increase the gain of the SDR-IP units by 20 decibels. Like that. And I can also reduce the attenuation in front of the units by 3 decibels. The noise floor, the white trace, is still minus 152 dB below the normal level of the carrier. The correlation gain is 27.5 dB, but I can see that the yellow and the green trace are equally noisy. They are spread over about 1 centimeter on the screen, which means that the noise is below at least 28. So summing up, 152, 23 decibels of reduced attenuation, and then 10 decibels loss on one side and 12 decibels loss on the other side in the notch filter I'm using. That means that the noise is at minus 164 dBc per hertz, and to that I have to add 28. And the sum of that is minus 192 dBc per hertz. And that is an upper limit for the noise of the oscillator. So I can do a normal sideband noise measurement to see whether I have AM or phase noise. With the current version of Linrad, the maximum bandwidth I can get with the SDR-IP units is about 12 kilohertz. And I can see here the phase noise, the correlation average. The yellow is at about minus 180, and I haven't waited long enough for it to stabilize. But the interesting thing is that the level of the phase noise is minus 155 without correlation. But when I go for amplitude noise, you can see it is much higher, particularly at close range. And this indicates there is a noise problem on the DC supply to the AD converter and introducing amplitude noise. So maybe I could do some more mods on the SDR-IP units. And here you can see amplitude noise and phase noise at the same time. Now when measuring the phase noise, the presence of some amplitude noise, 10 decibels, shouldn't change the result, but it would be nice to bring it down a bit. Well, after all, I could extend the range up to 24 kilohertz. So I will leave it running here for a while. And you can see the AM noise here. 5 hours is enough to reach the noise floor with the settings I'm using now. It is about 185 here for the phase noise, and the trace is very much jumping up and down, and I interpret that as there are digital spurs, and they are present also in the imaginary part, the red dots. If I switch for amplitude noise, it looks like this. Here the imaginary part and the real part have similar amplitude, and some parts are blue, means they are negative in the correlation. I can look at both at the same time, and then it seems that some places, like here, there is a spur that is present in AM as well as in phase modulation, means that this is a spur on one side of the signal frequency, and there are probably many more of that kind, and at lower frequencies they are strong, and these are the well-known spurs that reflect the separation between the carrier and the reference signal, and overtones, and things that I don't know. Something at 12 kilohertz, 6 kilohertz, well, 3 kilohertz.